So hello everyone, we are back again to our plasma class, and what will be starting today is the generalized Ohm's law. So nowadays what we are doing, we are dealing with the plasma fluid model. We started with our kinetic theory model, and then we are taking the moment of various order of the Boltzmann kinetic equation, and we obtained the conservation equation for mass, current density, and now we just in our previous class we obtained the conservation equation for momentum. Now we know that the thing that is bothering us in these derivations is the collision term. So the collision term, it is difficult to handle in case of our mass and charge conservation equation. What we did, it was rather simpler to tell that number of particles which are coming within the phase volume and the number of particles which are going out, they are more or less same, and under equilibrium condition we can assume that the net number of particles within that phase volume is constant, so that the contribution of the collision term is zero, so that we circumvented the problem. In case of momentum conservation equation, we found that there is no other way to escape from this collision term. So we tried to use the two fluid model where electron equation was having a term minus k, because they were colliding with the heavy species or the ionic fluid, and thereby they were exchanging the same amount of momentum with the ion fluid. So that way we put some minus k over here and the plus k over there in the ion momentum equation, and minus k in this electron momentum equation, and when we added them up, that cancelled, and that way we are saved there. So we are finding some way or other to basically exclude this contribution of this collisional term. Now we are coming to the generalized Ohm's law, and in that case basically we have no other way other than finding some model for this collisional contribution. So we will start with this equation anyway, and then we will try to model this collisional term k in some way, and finally we will reach to some equation which will resemble like Ohm's law, but it is a very generalized Ohm's law which is applicable in case of plasma, and we will see that under certain special conditions we can reduce this generalized Ohm's law into the Ohm's law which we know ordinarily, like J is equal to sigma E kind of equation. So we start with our this derivation of this generalized Ohm's law. So the electron momentum equation goes like this, and the ion momentum equation goes like this. So it is having MENE del V by delta T plus grad PE is equal to QE NE into E plus V cross B. So this is your Lorentz force term, and this is the collisional term, this is the pressure gradient term, and this is the unsteady term. Similarly, for your ions, you have this MINI del VI del T plus grad PI is equal to, so this is again the Lorentz force term, and this is the collisional term. And the previous our consideration is valid that the electrons are exchanging their momentum with the ion fluid, so this is minus k, and the same amount is getting added to the ion momentum equation, so this one. So we are having these two basic equations, and therefrom we will try to derive the generalized Ohm's law. So what first we do, we multiply the electron equation by minus E by ME, And similarly, we will multiply the ion equation, this one, by E by Mi. So when you do so, you multiply this one by E by Me. So E comes in the numerator, Me in the denominator, that cancels with this one. And because of this minus E, we have got a negative sign over here. And then Ne was already there and E has come just now. E is there and V was already existing there. So on the left hand side, the time derivative includes del t of minus Ne E into Ve. So this is on the left hand side. And then what we do, we have multiplied this by minus E by Me. So we do that and take it on the right side. So this becomes positive and it is E by Me and then grad of Pe. Okay. Now this third term, the lowering force term, we have splitted it into two terms. One is associating E and the other associating V cross B. And again we have multiplied by minus E by Me, and this QE you take as E because we are interchangeably using QE and E. And this is coming as this QE was already minus E and this is minus E by Me. So these are multiplied together and becoming positive, and so it is giving you E square into Ne divided by Me. This Me is coming at the denominator. So this E is there, and then same factor is coming because these two are having common factors. So E square into Ne by Me again coming here, and then Ve and cross B. And you see that we have multiplied by minus E by Me. So when we multiply minus K with this term, then it becomes E by Me into K. So this goes as far as the electron equation is concerned. Now we come to the ion momentum conservation equation, this one, and here we are multiplying by E by Mi. The things are very obvious. We are multiplying by the charge of the ion, which is positive E, and we are you can understand that we are considering only the first tonnage case, and then Mi is the mass of the ions. So when you multiply by this on the left hand side, Mi cancels, so Ni remains there on the top, and then E and Vi. So the time derivative is del T of Ni E into Vi, and that is equal to, now this has come to the right side and it is negative, and we have multiplied that by E by Me. That's why this term is staying as a negative term. Okay. Now what happens, when this is there, and then the other one term is similar to the electron terms, it will be coming obviously as E square Ni by Mi as a factor of E, and then you multiply by the same term Vi and cross B, and then the collision terms appearing here like this. One interesting thing, that this has now become positive because minus E by Me you have multiplied, and in the second term, this one in the second equation, it is also become now positive. So probably you are already thinking that now our plan will be, instead of addition, would like to subtract so that this term get cancelled, but that will not serve our purpose. In this case also we need to add these two equations to get something meaningful or something some insights into the problem. So this time we are not able to avoid this term by subtracting, we need to add this term. So K will essentially be there in the ultimate equation that we obtain, and so there is no escape. Now we have to model this K, and I will show you how nicely we can model this one realistically and get some useful information. So one thing is there, so when we are doing something model, so it is obviously not the exact phenomena, we are trying to model the phenomena. So it will be close to that one. It will mimic many of the features of the actual one, but for sure it is not exactly the actual one. So we will try to model this one so that we can get some realistic picture about the system behavior. We are not expecting that we will be getting the exact behavior, and for that probably we have to go for the numerical simulation where we don't bother about the complexity of the equations. We can just use numerical technique to solve the exact equation. So that will come in the latter part of this lecture on this fluid model. I will show you how these equations can lead to solution of exact practical problems, and that will be a real life problem, and what I will explain there, that how you can attack such problems and extract useful information through numerical simulation. So I will tell you the recipe about how you can get those solutions over there. But for the timing, what we are doing, we are adding these two. So if you add these two, you see that del del term, and in the argument it comes like minus NE into VE, and then this NI E into VI. This is coming here, and then you add these two, so E by ME and E by MI, this is negative and this is positive, and this one clubs together, it comes like this, and this E is taken common, so you see it is having E square NE by ME plus E square NI by MI as a factor, and then this E electric field is there, and then this one is E square NE by ME VE cross B, and this is E square N by MI VI cross B. Okay, and these two terms you can take K common, and then it is giving E by MI plus E by ME. So this is finally the equation that we get finally adding these two. So our aim is to get a Ohm's law. So you know that ordinary Ohm's law goes like J equal to sigma E kind of thing. So it must involve current density. And when we are looking for current density, then we cannot basically subtract these two. The current density expression is NIEVI minus NEEVE. This is because the electrons is having negative charge. Basically, you are summing our NIEVI. So E is negative for electrons, that's why this is coming negative and this is positive. So this term actually giving you the current density, and which would not appear here if we had subtracted these two. So we are here forced to add these two, even though we have now no clue about how we will model this K here, but if we want to have the current density, we need to add these two, and after adding we are landing up with this equation. Now I have just copied that equation over here so that you can directly compare. Now as I told you, this term is giving you the current density J. So this is del J by del T. Now this one minus E by MI grad of Pi. This term is E by ME grad PE, and this term is E square NE by ME plus E square NI by MI coming over here, and this is E, and this term is E square NE by ME into VE. So this is cross B, and this term is coming as it is over here, and this is one the K. Now I have circled two terms over here in red. Okay, so this is one term and this is the other term. What we will do, we will try to simplify this equation in a better way and in a more insightful manner, doing some approximation which are legitimate. So which are acceptable approximations. We will be doing that over here to simplify these equations and to bring it to a form which is meaningful and which gives us insight about the problem. And about this K, we will be modeling it. I am just giving you a clue over here that this K is basically the this momentum transfer through due to collision. K corresponds to, okay. So when suppose you are running and your friend is trying to catch you, so if you are maintaining a constant velocity between you two, then vi minus v is you are moving with one speed and your friend is also moving in the same speed, then this vi minus ve is 0 and you will never be able to catch each other and impact, okay. So if there is a difference in velocity, definitely you will be able to catch. So that is the same thing. If you want to impart momentum, that momentum will depend on the difference in velocity between you two, and how much momentum transfer will take place, that depends on some many factors actually. So that we put as a constant c. Now this term, this vi minus ve, you have it is this j is equal to nev. Here you can see that NEVE and NIVI, NIEVI, this was J, that J was over here, and if you are assuming a fully ionized plasma, then Ne equal to Ni and E is common, and then you can see that the current density is basically depending on the Vi minus Ve term, okay. So whenever we are finding that something is proportional to the difference Vi minus Ve, we can assume that it will be proportional to J and some constant, some other constant will be appearing here. We don't know what is the constant there, and to choose this constant in a self-consistent manner, we will do modeling for this case that will come in the next slide. But before that, we told that we need to rewrite this term square Ne by Me into Ve in a bit different way, making some approximation so that we reach some meaningful expression which can give us insight into the problem. So we start that, and here I am doing that Ne square by Me into Ve, that is equal to Ne by Me into NEV. You see that I have taken one E out over here, so NE is there and NEV is coming over here. And then what I have done here, I have subtracted this term NIE into VI over here, and then what I have done actually, I have added this term over here. What I am doing, you see that. So this NIE into VI, when I subtract, then it is giving basically NI square VI by ME. Okay. And here you see that MI cancels, then NI square VI by ME. So essentially what I have done, I have subtracted some term and added the same term over here. Okay. Now you can understand what we are talking so long, that NEV minus NIEVI, that gives you the current density. So E by ME into J plus E square by MI into MI NI VI is there. Now we have done a bit approximation over here. We have added this term ME NE into VE. You see that here this ME is the mass of the electrons. So it is more than 1000 times less than Mi. So compared to this term, if we are adding this term over here, then essentially we are not, compared to this term, we are adding some term which is really negligible. So we are introducing a bit error over here to reach some meaningful expression. So here we have, anyway, without any botheration, we have reached this minus E by ME into J as per our definition. And here, when you are adding these two terms, MI NI VI and ME NE VE, you know that this is, what is that? This is the center of mass velocity multiplied by mass density. So this is rho m into phi. So this is as per our definition. And this definition actually I believe that you remember, but still if you don't remember, then you can go back to our previous slides and you will see that we have defined that over there in the beginning of our this thing. This is the thing. So this is the V. Mi plus MENE V is equal to rho m into V. So this is the center of mass velocity, and we are just using that over here, and then we are trying to approximate this momentum transfer term. Okay. So this is here where we are now. So this is MI plus MENV, and we are putting that as center of mass velocity into multiplied by mass density. So these two terms are now here in place of this NE square by ME into V. So what we will do? Obviously, we will replace this term with these two terms, and we will try to model this collisional momentum transfer process. So one thing we have done, done for this this term, we will replace that with some of these two terms. Now remains that this modeling of this collisional term. So we come over there. Now here we will do a dimensional analysis to model the expression for K. So you just come over here, you see that here. This equation, so this is having del J del T, and then all these terms are there. You know that in a differential equation, partial differential equation, all the dimension of all the terms must be the same. So del G by del T, whatever the dimension of this term, should be the same as the dimension of say E by ME into K. Okay. So we just take that into consideration, that both this term del J del T and this term will have the same dimension. So we call this term as A, and we call this term as B in this expression. So A is equal to del J del T, so and B is equal to this term, what you have seen there. Now you know that if I remove E by ME also will have the same dimension. It is obvious. Now we come over here. A is equal to del J by del T, and we are all familiar that J is equal to NE into V. N is the number density, is the electronic charge, and V is the velocity. So this is the current density expression we all know from our electrodynamics classes. And in this dimensional analysis, you don't bother about the exact values. You just concentrate on the dimension. Okay. So I am just using this common expression NEV to make you understand that what dimension it represents. Now you take this NE and E out, then what you are getting? Del V by del T. What is that? That is acceleration. So this term is having a dimension of E multiplied by N and then acceleration. So we remember this term. Now this B is having a dimension of En and then K by N into Me. Now as I told you that we will model this K as some constant and then the difference in the velocities. That is what I just explained, that if you Vi equal to Ve, they will never able to impart any momentum. Like you and your friend both are having a gap, but you are moving at the same speed, so then you will never be able to catch each other. So that is the same thing. So they will never be able to impart any momentum unless there is a difference in the velocities. If they are same velocities, they are moving, then they will not be able to impart any momentum. So this momentum transfer will be proportional to Vi minus Ve. We put some constant C over here. E and N is there, and then N and M is there. So what I put over here again, that this Vi minus V will be proportional to J. So we put some another constant over here, and I rate J, and here you see that I am multiplying number density with mass of each quantity, okay, each electron. So this essentially gives you the mass density, so that is rho. Again I am telling you, just for sake of dimensional analysis, you take these quantities, not as per exact definition what we are doing. So this is just a number density multiplied by mass, so it gives you the mass density. And this is proportional to the current density, so we put some constant and J by sigma. So for dimension purpose, it will have a dimension of E multiplied by N, then J by sigma. We don't know what the value of C1 so far. Now, you compare with this one. A is having E and N and A, and whatever the dimension comes over there, that should be the same with En and C1 J by sigma. So if you compare En, here also En, then here is A is the acceleration and here is C1 J by rho. So what you can conclude over here is that C1 J by rho should have the dimension of A, which is acceleration. So C1 J by sigma should have the dimension of acceleration. Okay. Now we write it again over here. See, J is equal to sigma into E. You know, sigma is what? Sigma is the conductivity and is the your electric field. Now, if that is the case, then C1 sigma by rho into E we write here, and then we write here minus we have taken common and minus E into E. Then what is giving? E into E is what? Charge into electric field. So it has a dimension of force. So C1 sigma by rho into dimension of force. So that is what was coming in that expression. Now, so this is the C1 sigma by rho into dimension of force. Now, force is equal to what? This is mass into acceleration. Okay. So, what we got actually C1 J by sigma is equal to sigma E by rho, and that ultimately giving us some quantity multiplied by acceleration. And we have already concluded that this term, essentially this term, should have the dimension of acceleration. So here acceleration is taken out. So what this quantity should be? This quantity should be dimensionless. So C1 sigma by rho E into mi should be dimensionless. If that is the case, then C1 should have the dimension rho E by mi into sigma. You just put rho E by mi into sigma, then you will see that this quantity is becoming just 1. Okay. So now we are able to model C as, we can model it as this minus sign is not over here. I think it has gone out here. So I am putting it back here. So it is minus rho m E by mi into sigma. So if we put that as the constant C1, then we can model this as your C1 J by rho. Okay. So we model this K, this constant actually, you see that we model this term rho m E by mi into sigma. So rho m E by mi into sigma, what we just got over here, and then multiplied by J. Okay. So that is what exactly we wanted to do, that we want to model K as C1 into J, and then we wanted to look for C1, and we find that C1 can well be written as rho m into E by mi sigma, and then what we are getting? We are getting the a model for K as minus rho m into E by mi into sigma into J. Okay. Now we put that, and then finally what we get, we have put these two terms as I promised, that I will be putting this two term for this one, and for K I will put this term. So here we have now reached here. So these two terms are replaced over here, and this is for K, and what we are getting, this is the expression. So in the next class we will reach the final expression for generalized Ohm's law, and we will see that under what condition we can reduce the generalized Ohm's law into the Ohm's law which we know from our early days. Okay, so this much now, we will meet in the next class. Thank you.